Year 11. Tonight I'd like to go over questions 16 and 19 in the blue book, and I'll try and explain this as simply as I can. Please ask any questions as I go through, and I'll try my best to answer them. So the first one that we're going through is question 16, and here we have a typical guardrail. This guardrail has been fabricated, whereas some guardrails that you see have been cast. And it'd be a good idea when you're walking past some of these guardrails that have been put on bridges, just have a look at the difference between a fabricated one, in other words, it's been welded from parts, and the cast one, and you'll see the obvious difference. So what we've got here, we've got these sections here are called RHS, rectangular hollow section, and this here is a low carbon mild steel plate, and these are made from low carbon, and they'd have a carbon content of less than 0.3%, around about 0.1%, and we did this with introduction to heat treatment last week. Make sure that you know that mild steel that has a carbon content less than 0.3 cannot be heat treated to make it harder and tougher because it hasn't got the required carbon content in it. And the reason why they make this out of low carbon steel is because it's got a lot of ferrite in it, and ferrite absorbs impact because it's quite tough. And these are designed to absorb an impact and keep the car on the road, not to have it run off down an embankment. And the other reason is that low carbon steel is easily welded. If you start to weld carbon steel that's got greater than 0.3% carbon, you have to prepare it by preheating it. Otherwise, with its high thermal gradient, as the weld cools, it could embrittle the weld, forming martensite because of the high carbon content. So these are the sorts of things that I want you to learn. And if you have any problems, don't hesitate to email me or phone me, and I can explain it to you. So the first thing that we've got to do is determine the turning moment about point A created by the two impact forces. Now, when you're out having a look at these, you'll see some of these crash barriers have a larger diameter bolt at D, because when the car or the vehicle hits it, you're going to have a much greater force on this outside bolt here. And quite a few that I've seen have a larger diameter bolt where the force will be greatest. Okay, so the first thing you've got to do is determine the turning moment about point A, and they've actually told you what it's going to, where it's going to rotate there. Sometimes they won't, as I've said before. And so the first thing you do is, when we're dealing with moments, you always make a statement, the sum of the moments, and I've used anti-clockwise as negative here, which is unusual. I normally say clockwise is positive. I don't know why I did it here. And so we're going to add up all of the moments. Now, don't forget, we're not going to put equals 0 here, because all we're asked for is the turning moment about point A. We'll be doing that later on, saying some of the moments about A equals 0. And so this is the moment caused by this 120 kilonewton force. Remember, not very many people know what 120 kilonewtons is, the magnitude of it. And when you're dealing with kilonewtons, all you have to do is move the decimal point one place to the left, and that will tell you how many tons it is. And you know what a 12-ton truck looks like. So you can immediately relate that force to something that you're aware of. So we've got this force here, and we've got to find the perpendicular distance of this force along that line of action to that point there. So you look around and you see you've got a perpendicular distance here. So you've got to add 230 to 190 because you've got to go back to the pivot point. That's the lever arm of that force about that point to provide that moment or that torque. Remember, torque is the same as a moment. That's a twisting action. And so that's 120 times 420, right? And put it in, well, I've put it in meters here, so it's 0.42. And this is going in the same direction, which will be anti-clockwise there. And that's why I've put anti-clockwise there, so these will be positive, I guess. But I normally don't do that. And so you've got 95 times the perpendicular distance, 0.19. And so you've got the total moment produced by those two forces at operating at point A. And it's 68.5 kilonewton meters. Make sure that if you're going to give a moment, it's got to be Newton meters, and don't leave out the kilo because we're dealing with kilonewtons there. Okay, so that's the answer to 1. 2, determine the shear force acting in the two anchor bolts C and D. Now, remember that shear is trying to move one surface over another, and it hasn't got anything to do with turning. It's just horizontal forces here. And so that force plus that force has to equal the shear force in those two bolts there. And so we've got some of the forces in the X direction with that direction positive. And so this has to be in the opposite direction, because if those forces are going in negative direction there, the shear force in these bolts here, a reaction would go in the opposite direction. But we're only asked to find the shear force in them. We're not asked to find the reaction. So I've put negative 120, that's that one there, negative 95, and so we've got the total shear force is 215 kilonewtons. Now, don't forget it's not kilonewton meters because this is a force here. So it's equivalent to about 21.5 tons. And the negative tells you that it's going to the left. So there's our horizontal shear force, and you can show it by that there if you like, or you can just put a negative there because you've said that going to the right is positive. But that's the easiest way of doing it. The next question, question 3, assuming the shear force to be the only force acting on the bolts, find the shear stress in each of the two anchor bolts. So the anchor bolts have a diameter of 25. So make sure that you can remember this. This is how you annotate a bolt. It's a metric thread. That's the profile. It's 25 diameter, and the pitch is 3.5. So that's the distance between one peak of the thread to the adjacent peak of the thread. And so the bolts are 25. This is how I want you to set it out as I explain each time I go through these. So the shear stress is equal to load over the area of shear, and put your data here and make sure that you don't put kilonewtons in there, because you could forget it and you'll be 1,000 out. So write it out in full, put the units there, because remember you're explaining to the examiner how you did this if you've got a wrong answer here. Now the area is normally pi r squared for one bolt, but it's 2 bolts, so it's 2 pi r squared. And I normally work that out, but I haven't here. But I think it's a good idea to work it out so that you don't have to transfer 1, 2, 3 things. You just transfer one thing. And I don't normally put 10 to the minus 6 there because I want my answer in megapascals. And so the shear stress in each bolt will be 219 megapascals. And a bolt that isn't a high tensile bolt, it's just a low carbon steel bolt, would probably have a shear strength of around about 240 megapascals. So it's getting up there. But these would, I guess, be high tensile bolts if they're designing it for these forces here. Okay, that's part A. Now, part B, for another impact, the combined horizontal force acting on the guardrail is 150 kilonewtons. So the horizontal force acting on the guardrail now is 150 kilonewtons, about 15 tons. The moment about A that results is 51 kilonewton meters anti-clockwise. Now, the question asks you to sketch the force and the moment that must be provided at the base of the guardrail to maintain equilibrium during impact. So this is a reaction force. And so if you've got 150 kilonewtons acting to the left, the reaction to that force on the guardrail must be 150 kilonewtons to the right. And the moment is 150 kilonewtons anti-clockwise. And so the reaction to that has to be 51 kilonewton meters, don't forget meters, clockwise, so that it keeps the guardrail in equilibrium. And next question, during impact, assume the tensile force resulting in anchor bolt D to be 4 times as great as the tensile force in the anchor bolt C. So this is absorbing 4 times the force of this bolt here, the tensile force. And it will be a tensile force because this guardrail will try to rock anti-clockwise and it will pivot about A, so it'll be trying to pull that bolt out or break it in tension. Determine the tensile force in anchor bolt D at the time of impact. So you let the force in bolt D be T, and the force in bolt C will be a quarter of that, because this is 4 times the force in that. Take moments about A, and you have one unknown in the question. So some of the moments about A equals 0 with clockwise positive. So we've got T over 4 multiplied by 0.07. Now remember that this is that perpendicular distance there, and we've converted it to meters, so that is 0.07 meters. And then this one here is T times 0.25. Now remember, you've got to go right back to the pivot point. So you've got to add that to that. This is a common mistake that lots of students make, particularly when you're not experienced in reading drawings. And a lot of students find it hard to figure out these dimensions. And that's why you've got to constantly practice graphics in this course. And so, the reaction force there is 51 kilonewton meters, and that equals 0. So because we've said that the sum of the moments equals 0, we've got this force in the inside bolt, that moment in the outside bolt and the moment on the guardrail is going anti-clockwise. So that is 51 times 10 cubed, which has been given to you, 51 kilonewton meters there. And remember, this is a reaction. This is the reaction on the bolts. And so that equals 0. And so you've got one unknown here, and you'll be able to find the tension in bolt D. Yeah, and obviously it's in kilonewtons. It's not kilonewton meters because that's a moment. So it's a tensile force in bolt D. Let's have a look at question 19 now. I remember this was given in HSC quite a few years ago, and it caused a lot of problems. So question 19, a uniform solid cylinder, circular cylinder, diameter 1700 millimeters and height 2100 millimeters, has a mass of 500 kilograms. It stands vertically on a rough horizontal surface. Now note that I've put millimeters there and millimeters there. Normally you don't need to do that, but in this question, if you find that it enhances the information to the student, you can put millimeters in. But normally, millimeters are the standard unit for engineering, and so you don't really need to put it in. But if you want to put it in, you can. And it's got a mass of 500 kilograms. Now, don't forget, that's not a force, that's a mass. It's the degree of compaction of the particles. If you took this cylinder up to the moon, it would still have a mass of 500 kilograms. It stands vertically on a rough surface here. Now, I've missed out P there. P is this force here. Determine the magnitude of the horizontal force P applied to the top of the cylinder as shown in the diagram, which will just tilt the cylinder. Now, it's not a bad idea to just quickly sketch it like this. So does it say that they haven't given you what it's going to pivot about. So this is a bit of engineering acumen that you've got to develop. So if you're applying a force there, you know it's got to pivot about that point there. And it's on a rough surface, so it won't slide. When they say a rough surface, it means that it would, the force of friction will be large enough for it not to slide. Okay, so we've got A there, and so you say some of the moments about A, you know that the 5 kilonewton force goes down because I've multiplied that by 10. So that's 5,000 newtons. And make sure you only use 10, don't use 9.8 like you're expected to use in physics and maths. We use 10 for the acceleration due to gravity. So that's 5,000 newtons, so it's 5 kilonewtons. And so you say the sum of the moments about A, make sure you tell the examiner where A is, equals 0 with that direction positive. And so we've got P times 2.1. Now the height of the cylinder is 2.1 meters given to you in the question, and that's the perpendicular distance between that force and that point there. And that's going to go anti-clockwise. It's going to rotate anti-clockwise. And then you've got this force balancing it. So that's 5 times the radius, which will be 1.7, which is the diameter, divided by 2. And so we've got that force multiplied by that distance, and that equals 0. And so the force P to just tilt the cylinder is 2.02 kilonewtons. Now, I generally don't go to 2 decimal points, so I try to keep it to 1 decimal point. I was marking a CWR last week, and this person put it to 6 decimal points. Now that's just a waste of time. Keep it down to 1 decimal point. And you know the rule, if it's 5 or greater, the next decimal point goes up 1. Question 2, it asks you to determine the magnitude of the smallest force necessary to just begin to tilt the cylinder. And so if you want to apply the smallest force, you've got to have the biggest lever arm. And so you still have to apply the force at P there. And so the biggest lever arm will be this diagonal. And so by using Pythagoras, you can find that distance. That'll be the perpendicular distance. So d squared equals the diameter squared plus the height squared. So we've got d equals the square root of 1.7, which is the diameter, and plus 2.1, which will be the height. So that's the diameter, and that's the height. So d is 2.7 there, whereas remember, it was only 2.1 before, so you had a smaller lever arm, so therefore you have to increase the force. Some of the moments about A, make sure you put A there, as I mentioned before. So we've got this P minimum is going anti-clockwise, multiplied by 2.7, plus the weight force acting through the center of mass. They'll always give you the center of mass if it's not obvious here. You know that the center of mass goes through the geometric center of the object. So you just draw 2 diagonals there where they join. That's where the center of mass is. It's the centroid of this particular object. So that equals 0. So P minimum is equal to 1.57 kilonewtons. And here we have 2.02 kilonewtons. Now, normally, this should be go up to 1.6 kilonewtons there for 1 decimal point. Okay, I hope you understood all of that. If you have any questions or any problems with any of the CWRs, make sure that you contact me, and I'll do my best to answer. Okay, thanks for listening, and I'll speak to you next week.